Hi everybody, we're back for a support today. So we're just going to be talking just briefly about the concept of set theory today. So set theory sounds like a pretty weighty topic to be diving into in an introductory statistics course, but we're really just covering the very basic stuff, the set theory that you can see oftentimes in probabilities, which of course we know we've seen already and we will continue to see for the rest of the semester. So we'll get a little bit of notation in here today, but primarily it's just understanding that the basic concept of what a set is and how they can interact with each other. So to start us off, so just defining what a set is, so we say a set is a collection of distinct objects. And that's it. Okay, it's just a collection of distinct objects. So there's nothing too crazy, too special about it. It's just a group of objects, a group of stuff. So in the context of statistics, it's usually data points. Data points lie within a set. So, for example, we're going to have here a couple of sets. So A, that's going to be our first set. If I can get the right, there we go. So we're going to say A is the set 1, 2, 3, 4, 5. Okay, close that out. And then B is going to be the set 0, 2, 4. Okay, so this is the data sets that we're going to work with. So in terms of notation and the operations that we can perform on sets. So the first couple that we have here, so we have this symbol. Oops. So it looks like AUB. So this symbol here, this is our union symbol. So this is A union B. And what this signifies, so A union B is going to be all elements in A or B or both. So when I say the union of two sets, I'm talking about basically A or B or anything in either of them. Okay, that's the union, is all included within the union. The next one is, looks like an upside down U, but this is the intersection. So we would say A intersect B, but the intersection of two sets, this is elements that are only in both A and B. Okay, so the union was elements in A or in B or in both. The intersection is only the elements that are in both specifically. Okay, and then the last little piece of notation here, that would be when it looks like A to the C power, right? It's not a power, but what that C stands for is complement. So this is a probability rule that we've looked at, right? And this is how we would write it using set notation. So this is a complement. So basically, all this is telling us is when we have the set A, the complement is elements that are not in A. Okay, so A union B, They're in both A or they're in either A or in B or in both. A intersect B is only the elements that are in both A and B simultaneously, and then the complement of a set is all the elements that are not in that set. Okay, and then we can also see, so sometimes we'll use an S, and this would be known as the universal set. It's also called U sometimes. So universal set. But we, in statistics, generally call this the sample space. So the sample space, if you remember from early on in chapter 1, that's just all possible values. All possible values of data makes up the sample space. Okay? So, for example, if we're working with these sets up here, okay, so we're looking at A is 1, 2, 3, 4, 5, B is 0 to 4. Well, then in this case, so A union B, that would be everything that is in A or in B or in both. So I'm just going to take every value from both of them. So that's 0, 1, 2, 3, 4, and 5. Notice I didn't repeat anything that shows up multiple times. That's fine. We just write it in there. I just want to know which values are in it, not necessarily how many times they show up. Okay? And then A intersect B, that's going to be all the values that are in both A and B. So if we go back up and look, all the values that they both share, that would be 2 and 4. Right? Those are the only values that they both have in common. So the intersection would just be 2 and 4. Those are the only points that they both share. All right. And then a complement. So all the values that are not in A, well, there's only one value out of all of these that's not in A, and that would be 0. That's the only value in A complement. B complement, all the values that are not in B, that would be 1, 3, and 5. Now, we can represent these sets using what we call Venn diagrams. We did look at these briefly in class back when we were talking about the probabilities and these sets like this. But basically the Venn diagram, we create a rectangle that's going to be our sample space or our universal set. And then we're going to create some circles within that. Let me thin those circles a bit. Okay. So there's one. And there's 2. Okay. So these circles are each going to represent one of the sets. Okay, so there's A. Oops. And over here, there's B. So those are our sets. And then, of course, the universal set is out here. So that's our sample space is S. So that would be everything that's not in A or B, right? But it includes A and B. They're both inside of S. So now if we were looking at the values in our specific example, Well, the values that A has that B does not have, those values would be, right, 1, 3, and 5. The values that B has that A does not, that's just 0. And then the values that they share are 2 and 4. Okay, and this is how we would write this out as a Venn diagram. So if we're talking about these different sets, the intersection and the union, well, the intersection is quite literally the intersection of the circles. So that's going to be A intersect B. Okay, so the intersection is where they overlap, so that's just this portion. The union is going to be everything that's in A or in B or in both. So it's anything that's in the circles. If there was another value that did not lie within A or B, so for example if 6